Inside a sealed container of pure liquid, molecules at the surface are constantly breaking away and rising into the empty space above, transitioning from a liquid state into a gas. Because the container is sealed, those escaping molecules have nowhere to go. They eventually lose energy, collide with the container walls or the liquid surface, and cool back into their liquid state. Eventually, the system reaches equilibrium, the exact moment when the rate of molecules evaporating perfectly matches the rate of molecules condensing. During this state of equilibrium, the vapor bouncing against the walls of the container exerts a specific, measurable physical force. We call this vapor pressure. The strength of that pressure is dictated by microscopic intermolecular forces. If the bonds holding the liquid molecules together are weak, they escape easily. A high rate of vaporization creates a high baseline pressure. Conversely, liquids with strong internal molecular attraction hold their molecules in place. They restrict evaporation and generate a low baseline vapor pressure. We can observe the interplay of these forces when we introduce a second, completely different volatile liquid into the closed system. Logic might suggest that mixing two liquids yields a predictable outcome, but the resulting total vapor pressure of a mixture almost never equals a simple, straight average of their individual pressures. Instead, the liquids react. Anomalies in the resulting vapor pressure, accompanied by shifts in total volume and temperature, act as a diagnostic map for chemical affinities. Macroscopic physical properties like pressure, volume, and heat are direct, measurable readouts of invisible microscopic forces. To read that map, we need a baseline. In the late 19th century, François-Marie Raoult set out to establish a mathematical rule that could predict the exact vapor pressure of any binary mixture. At the time, studying chemical thermodynamics required tedious empirical measurement. Researchers used intricate networks of sealed glass to physically extract and isolate pressure data. Through this exhaustive measurement, Raoult identified a strict proportionality. He established that the partial vapor pressure of each individual component in a mixture is directly proportional to its specific mole fraction. This chart maps concentration, or mole fraction, on the x-axis against vapor pressure on the y-axis. The pressure of our first liquid rises in a perfectly straight, linear line as its concentration increases. When plotted mathematically, the expected total pressure of the mixture forms a straight line directly connecting their peaks. It is a perfect additive sum. Any chemical mixture that perfectly follows this straight line math at all possible concentrations is defined as an ideal solution. For an ideal solution to exist, it must meet a strict microscopic requirement. The forces between the different molecules must be identically matched to the forces holding the same molecules together. Because the bond strength remains identical, the first thermodynamic consequence is that mixing requires zero energy exchange. No heat is absorbed, no heat is released. The change in enthalpy is zero. The second consequence is spatial. Because the molecules attract each other with the exact same strength, the liquid neither expands nor contracts. If you mix 50 milliliters of liquid A with 50 milliliters of liquid B, the total volume is exactly 100 milliliters. Mixing n-hexane and n-heptane yields this exact result. Ideal solutions represent purely statistical additive mixtures. The introduction of a new chemical changes absolutely nothing about the internal physical forces.
In reality, the vast majority of chemical mixtures are non-ideal. They actively disobey Raoult's mathematical straight lines. Look at this total pressure curve bowing upward above the expected straight line. The vapor pressure generated by the mixture is higher than the math predicts. We classify this upward arching gap explicitly as a positive deviation from Raoult's law. The microscopic cause here is an active rejection. The newly formed bonds between the two different molecules are distinctly weaker than the original bonds they had with themselves. Because the different molecules mutually repel or simply fail to hold on to each other tightly, a surplus of molecules rapidly escapes the liquid and floods the vapor phase. Volumetrically, weaker bonds mean the molecules drift further apart. This active structural expansion increases the total volume of the mixture. Thermally, breaking strong initial bonds to form weaker ones requires absorbing energy from the surrounding environment. The process is endothermic, cooling the container. You can observe this reaction directly by mixing ethyl alcohol and cyclohexane. A positive deviation in pressure, an expanded total volume, and a drop in temperature are all interconnected proofs of weak molecular affinity. Let's pivot to the opposite extreme.
liquids that exhibit a profound, tight affinity for one another we mixed. Watch how this tight affinity breaks Raoult's law on the chart. The total pressure line sags deeply beneath the expected linear reference. This sagging curve defines a negative deviation. Microscopically, the two distinct molecules are forming stronger links, often powerful hydrogen bonds, with each other than they did alone. Because the molecules lock each other in a tight grip, they essentially trap one another in the liquid phase, drastically starving the space above of any vapor. These stronger bonds physically pull the molecular structure closer together, noticeably shrinking the total volume of the mixture. The spontaneous formation of highly stable bonds releases excess energy. The process is exothermically active, heating the container. Mixing chloroform with acetone is the classic case study for strong mutual affinity, generating immediate, measurable heat. A negative deviation, a shrunken liquid volume, and a spontaneously hot container serve as the definitive physical signatures of intense molecular bonding. This side-by-side chart displays the full diagnostic spectrum of chemical mixtures, the perfectly linear ideal state, the upward positive deviation, and the downward negative deviation. Each curve links perfectly to its macroscopic thermodynamic values for enthalpy and volume. These measured properties function in a predictable sequence. An exothermically heated mixture indicates that strong bonds have formed between different molecules. Those bonds hold the liquid together more tightly, which restricts vaporization and creates a negative deviation. Applying that same logic to the inverse, an endothermically cooled mixture indicates weak bonds. Weak bonds fail to trap molecules, allowing rapid vaporization and creating a positive deviation. Variables like changes in heat, changes in volume, and total vapor pressure cannot be treated as isolated data points. They are inextricably linked physical reactions. Raoult's linear equation provides the essential theoretical yardstick that makes detecting these physical anomalies possible. The complex, invisible interactions of the molecular world can be perfectly categorized and mapped simply by measuring the pressure of the vapor resting above them.